Any vector can be broken up into two vectors which are at right angles to one another. So in essence, when we're looking at components of vectors, we are looking at the two parts of a potential resultant. Perpendicular means they must be at right angles to one another. So what we're going to now investigate are things known as the vertical and horizontal components of a vector. So let's say we are holding the dog's leash over here. As you can see, we're holding it at an angle. It is the same holding this leash at one angle. That is the resultant of a horizontal and a vertical. If somehow we could have two leashes on this dog, one pulling to the right and one pulling upwards, it would result in a single angle going up, a resultant vector. So kind of what we're doing now is really the exact opposite of what we did before. Previously, we had been given two vectors. They would be at 90 degrees to each other, and we would calculate the resultant. Now we've in essence been given the resultant, and we expected to calculate the two vectors that would make it up. So, in this example, resolve a displacement of 100 meters on a bearing of 70 degrees into its components. Let's say we did this by scale diagram. We could say 1 centimeter represents 10 meters, and then we would draw a 10 centimeter line at an angle of 70 degrees from north. In other words, on a bearing of 70 degrees. We would then complete a parallelogram around that diagonal. Because I'm pointing up towards the top right-hand side of the page, I would have a right-hand horizontal component and a upward vertical component. Since I have to complete an exact parallelogram, that would define the length of these two lines, and it turns out that this line would need to be 9,4 centimeters and this line 3,5 centimeters. By scale diagram, remember your answer might not be 100% accurate. The 3,5 centimeters would convert into 35 meters north, and the 9,4 centimeters would convert into 94 meters east. It would be much more accurate via a calculation. So if I'm doing a calculation, I first draw a rough sketch. By rough sketch, it does not mean you can ignore the ruler tool. You need to get a ruler, you draw the diagram, it just doesn't have to be accurately measured. So I draw my 100 meters up there, I put in a vertical, I put in a horizontal. If I look at that then, I can put in the 70 degrees it's on a bearing of, and now I have got an opposite side and an adjacent side and a hypotenuse using this triangle over here. Now if I am doing a calculation, I am going to say I am interested in my adjacent side, the vertical component. So I am going to say cos of 70 degrees is equal to my adjacent over my hypotenuse, vertical component over 100. I punch in cos 70 degrees multiplied by 100 and I get 34,2 meters north. When I am trying to find the opposite, which is exactly the same, I like to work in the same triangle. Some people like to work first by saying, okay, well, if this angle over here is 70 degrees, this angle over here must be 20 degrees. And then they use cos, because the horizontal component is the adjacent in the bottom triangle. I personally prefer to just work out what is the opposite in the triangle I was working in before. That means I need to use sine, opposite over hypotenuse. So sine of 70 is the opposite over the hypotenuse. And when I look at that, I have got my opposite side, which is what I don't know, over the hypotenuse, which is 100, sine of 70 degrees, and then I go sine 70, punch it into the calculator, multiplied by 100, and I will get 94 meters towards the east. Now I've got a boy and he is sliding down a bank. That bank is inclined at 30 degrees to the horizontal. So let's draw that. 30 degrees to the horizontal, and I am told that the bank is 5 meters long. That is the actual bank. Now what they ask me is, what is the height of the bank? So this is the length, so that is a horizontal component. If I go up here, I will get the height, which is a vertical component. So that becomes my height. And I land up with a parallelogram around there. I'm only interested in the vertical component. That's my vertical component. So I'm going to label this triangle opposite, adjacent, hypotenuse. And I'm going to say, if I am interested in this height here, then I am going to go opposite and hypotenuse. I use sine. Sine of 30 degrees is equal to my opposite over my hypotenuse, and my hypotenuse is 5 meters long. So I punch in sine 30 multiplied by 5, and I find that I get a 2,5 meter high bank. This is the diagram. You can quite clearly see 5 meters, 30 degrees, and my opposite side is going to be 2,5 meters. This was drawn to scale, so that was a 2,5 centimeter line, which converted into 2,5 meters with a scale of 1 centimeter to 1 meter.